All right. Can you see this from back there? Otherwise, you might want to hit the third button on that white box there. That'll turn this front light off. There'll be less glare. Is that better? Ish? All right. So let's start off. So on Blackboard, we'll go through the syllabus first. So under content, you see there's a whole bunch of crap here already. We're already operating off of the new course standard for the new master's program. So our program is going to be, instead of a bunch of 16-week classes, it's going to be a bunch of 8-week classes. So you've enrolled in a 16-week class. The first 8 weeks will be one subject. The second 8 weeks is going to be a different subject. So the first 8 weeks we'll be doing computer organization and architecture stuff. Second 8 weeks we'll be doing data science stuff. The textbook for the class is up on Blackboard over here on the far left. If you click on textbook, gives you the instructions. Go to Zhai Books, and there is a book for the class, and it has all the text you need for the whole class. It has the data science stuff in it as well as the architecture stuff in it. So the book will end up looking something like this, where you have the first 8 weeks we'll be doing assembly stuff, architecture stuff, and then the rest of the time we'll be doing stuff with data. All right, so kind of treat it like two separate courses. The one downside to that from a typical Littman course perspective is that doesn't mean that that means that your final exam can't replace your midterm exam, because your midterm exam effectively is a exam over a different subject than your final exam. So we can.
But we end up with one grade then?
It'll be one grade, yes, between the two of them, because we don't have two classes to give grades for. So probably just be really good at both. That's what it comes down to.
Is that how you're doing the undergrad courses now too?
Or
is that just us?
That's just, well, it should be the both grad classes. It's possible that Bob hasn't so directly separated them, but his class should deal with database stuff and security stuff as two kind of broader subjects, I guess. I don't necessarily know what he's doing. Undergrad will be updated in the next year, and this will be official next fall. So we're just making the transition now. Okay, so that's the textbook. I don't know what it costs. I don't know, like $60, something like that.
Did you say next year or next semester?
Next year. I mean, next semester I'll still do my class as it'll be 6 credits, but you'll still do, yeah. From your perspective, it really isn't a difference.
Well, it might affect whether I can get reimbursed.
Oh, well, I thought they approved both this semester.
Yeah, but I think they only let me take 2 classes. This is 2 classes, but if it was like 4 in a class.
Oh, I see what you're saying. Yeah, well, even when it's 4, it would only be 2 at a time. But I get what you're saying. That could create a weird challenge. Well, I'm sure we could figure it out one way or another.
Each class is still going to be 3 credits, right? Like it's just
For the rest of this year, it'll be, every class will be 6 credits. Next year, it'll be 3 credits per class, but you'll have a class the first 8 weeks and a class the second 8 weeks, and like that.
It still would be a 3-year program, though?
Yeah, everything will be identical except the subjects will officially be separated. Okay, so back in the syllabus here. Blah, 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 usual crap. Grading scale, 60% homework and quizzes, 20% midterm, which is the final exam for computer architecture, and 20% for the final exam, which will be the final exam for the data science portion of the course. Okay, the rest of the stuff is read through it, just the whole, background, learning outcomes, stuff like that. So feel free to memorize that, whatever. So questions about the grade breakdown. If it's not an exam, it's worth 60% of your grade. If it is an exam, it's worth 20% of your grade. all your exams together are worth 40% of your grade. And it's the usual 90, 80, 70, blah, blah, blah scale. All right, so now, all this extra crap. You are cordially required to, so our Grace group, which is our ACM group here on campus, we're hosting 7 Tech Talks this semester. All the dates are up here. First one is next Wednesday night, and then they're staggered every 2 weeks after that. And we're bringing in a speaker from off campus that's in the tech industry. And that speaker, there'll be food and stuff there, but that speaker is going to be educating on what industry is really like, and what we've instructed them is to kind of talk to the audience as if they're speaking to like their 20-year-old self. What advice would they give to their 20-year-old self? So these are going to be many of them are leaders in the tech world. So if you wanted to bring a resume or something like that, they might be willing to take your resume or give them a business card or something like that. If you wanted to follow up with job type things. First Tech Talk next Wednesday is a guy named Mike, who is the head of software engineering at SkyTech here in Mequon. And several of our students have interned there. We have a couple of them are still interning there, so it's possible he's also looking for or can get you connected with somebody for an internship or something like that. Let's see, we have some folks from Acuity coming 1 week. Which is the week you guys are doing it? All right, so this 10-2 one are some upper managers from Acuity are coming down. And then kind of the same style talk. And then 2 weeks after that, we're having some alum from the computer science program at Concordia who work at Acuity come down and give us the former CS employees' perspective of what it's like there and that kind of stuff. We have speakers booked for every event except for this last one. So as soon as I get that one, I'll probably release the names of all of them, but I'll give you some information about each one the week leading up to it. So you are required to come to these events and they're from 6 p.m. until roughly 8 p.m. Let's say. We're going to run them as like traditional meetups where there's like maybe a 30-minute period for like networking and talking to people. And then there's going to be like a 45-minute to an hour talk. And then kind of a time for questions, answers. If you are not able to make the event or just don't want to come to it, you can instead research their company, write a 4-page paper. Who is the speaker? What does their company do? What kinds of tech-related jobs are available at the company? What skills does a person need to get a job there? And whether or not you'd consider working there, why or why not. So you can choose to write a paper. You can choose to come to the event. I suggest you come to the event so you get to meet these people. If you come to the event, you just have to write a couple of paragraphs and submit kind of a summary of how you can apply that to your future decision making for getting jobs.
So the numbered questions are for just if you're not able to go?
Numbered, correct.
Okay. So
Yeah, if you read the things here, it's pretty clear. Yeah, either go and write 2 paragraphs or write a 4-page paper that covers these 5.
I was just confused because if you don't go, how are you? Well, you just mean.
I'm going to be
the
telling
company?
you,
Okay.
yeah, I'll be telling you who the speaker is and what company they're from.
How long did you say it was going to be? Like, as far as time? Like,
2 hours, 6 to 8 p.m. max.
and are we supposed to look halfway decent?
I don't think it matters. It depends how you want to present yourself. I mean, I don't think it matters. I think they're coming with the expectation that they're going to be talking to students who are likely stumbling down from their dorm or something like that. So I don't think they expect you to be all dressed up or anything, but you want to snazz it up, that's up to you. You know, go up and slap them with a resume, slit their tires, whatever. Okay, so those are the Tech Talks. There are 7 of them. All the dates are out there now. So feel free to mark those off on your calendar, try to get out of work, whatever, all that stuff. If you don't want to come to them, that's on you. There's an alternative assignment, so you won't get penalized. All right, questions about the Tech Talks. I'll also be releasing a list of leadership talks that are being run by the MBA program. I'm not requiring those, but I'll encourage you to go to those talks. Other, again, business leaders, some of them are in technology, but I'll make you aware of those events, but you don't have to attend those. All right, and then we have our required hackathons. Notice it's plural. In the past, we've had an internal hackathon here, and we have that this year. We have our Lady Ada hackathon, which is October 5th from 8 a.m. to 8 p.m. And that's going to be here on campus. Now, all these events are going to be over in the new business building. So computer science has a space over there, and it's called the Collaboratorium. And that's where the speaking events are going to take place. That's where our hackathons will take place. So instead of being here in the department, they'll be over there in the new building.
The TikTok was on.
All of them, tech talks and the hackathons, all of it. In fact, if you want, maybe somebody remind me at our first break or something like that. We could take 5 minutes and walk down there. I can give you the nickel tour, and then we'll come back. We'll just stay a half hour late. All right, so this is going to be our typical hackathon. For those of you who haven't come to these before, we break everybody into a bunch of groups. We usually put some stronger programmers in. It's kind of a programming competition, but it's only among Concordia students. So we'll put some stronger programmers in groups with some weaker programmers, and then there's kind of a global goal. And then the hope is that at the end of this 12-hour period, you've learned something, gotten a little bit better at some of these things, whatever. Now, this other one, the Batterman Battle Hack, is a traditional 24-hour hackathon, and this is scheduled the Friday night, Saturday night, prior to Startup Week Milwaukee. Startup Week Wisconsin, technically, but we have a more local chapter of that called Startup Milwaukee. So there's going to be a lot of different players kind of in town for that. So the hope would be that we're going to get some folks that are not Concordia people. We already have another university, Elmhurst College from Chicago area, Elmhurst, that is going to bring all of their computer science students up here for that. And so we'll definitely have at least one more school there, but we're going to market it through our internal marketing as well as the Startup Milwaukee is going to market it as well. We have Sargento as one of the sponsors, so I suspect there will definitely be cheese. We're talking to Acuity about sponsoring something, and we have a couple of other local sponsors that are going to help provide something. But this will be our traditional 24-hour hackathon. We will help create groups for this if you're interested in being put on a team. Otherwise, you can form your own teams, because the idea would be that some folks might be interested in, going and maybe joining a team with the Elmhurst people, or some folks from another school, something like that, and getting to know some new people, whatever. So we won't lock you into anything there, but we are happy to help you get onto a friendly team if you want it to be more of a learning experience, I guess. All right, so notice here for both these hackathons, if you cannot come to the hackathon, there is an alternative assignment. The first alternative assignment for the Lady Ada hackathon counts as 3 assignments. So that hackathon counts as 3 assignments. So the penalty paper for that is insane. It's typically been like a 12-page paper or something like that on a pretty crappy topic. As you might see here, the battle hack, it actually counts as 5 assignments. So if you come to the battle hack, you're going to get credit for 5 homework assignments in the class. If you don't come to the battle hack, imagine if a 12-page paper is 3 assignments, how many pages is 5 assignments when it's Mr. Gonzalez doing the math? Not good. It's probably a 90, 100-page paper. Double-sided, size 2 font. Yeah.
The battle hack, what are the rules to assembling a team? Do they have to be Concordia students that are currently enrolled? They can be from
anything. We'll probably hopefully we'll have some professional developers there. Yeah, anything goes. We want it to be a big experience. The reason we called it Battle Hack for, I think did we ever do Battle Hacks when you were around?
I vaguely
Okay. we used to travel around the country for this big hackathon that PayPal put on called Battle Hack. And they had 14 hackathons in 14 different cities across the world, and 4 of them were in the United States. And we would travel to all 4 of them, or at least 3 of them in the United States. Blade came, that's Blade, by the way, he's Chinese. He came to several of them.
I joined.
It's recorded. You went to Chicago, and you went to New York, and Raleigh.
Yeah, Raleigh.
So, yeah, so these were put on by PayPal. It was a hackathon done right. The awards were these big battle axes. If you've ever noticed on my Slack account here, and I'll get everybody on Slack as well, but if you've ever looked closely at my picture here, that is me holding battle axes from Battle Hack. Okay, and and Maddie, do you see the axe in the back? And then you see the little shoe back behind me? That's the shoe of Amish. that's in Raleigh. So that's the trophies for the hackathon when we used to do the battle hacks. And the story with the Raleigh one is we needed extra funding to get there, and PayPal, we were crowdfunding it, and PayPal paid our way, like in the last moments. I made a big story about it. But anyways, it was actually a company called Braintree that was putting on those hackathons, which is was a PayPal company. As soon as they split and it was no longer a PayPal company, they stopped doing the hackathon. But the way the thing worked is there was 14 hackathons in 14 different cities. The winners of each hackathon came together at PayPal headquarters for the World Championship. Now, year 1, we're probably not going to accomplish that, but we're going to try to have a closer to a real deal big 24-hour hackathon at this one. We're going to hopefully replicate some of the things that we were able to get done with they did at the Battle Hacks. Battle Hacks had like a massage room where they would do shoulder massages, and they brought in food trucks, like Better Food. We won't be able to do the alcohol part because we're a dry campus, but most of the other things we'll hopefully get sponsors for. All right, so questions about those required events. And people do sleep at the 24-hour hackathon. Some people don't, but there's usually like a quiet room with some air mattresses or something like that. So it's not uncommon for somebody to go take a couple-hour nap or something. But there's plenty of people who stay up all 24 hours too. But you won't be, if you just can't function like that, it's not going to be the end of the world. People sleep. All right. Questions about any of those things? All right, then, if you've had my classes before, we have Bible homework. I've already put up all the Bible homework for the semester. So if you want to knock it out, you can. One of my goals is that if you get into the habit of reading stuff from the Bible, at this point I'm giving you points for doing it, but once you're no longer getting points for doing it, maybe this becomes a new habit that you stick with. So if you just want to go through and there's 14 assignments, each one's to read 2 chapters from Book of Matthew, and you have to write a couple of paragraphs kind of reflecting on it. I did change a little bit of how I want you to reflect on it from before, so not drastically. So I said if you are able, write a few paragraphs reflecting on what this means to your life, not just what it relates to, how it relates to computer science. I said if you are able, also try to connect this to your vocation in computer science. And I said, note that some chapters may have strange and very hard to apply content. For those, please make your submission as appropriately funny as possible so that I'm convinced you did actually do the reading. Because we've had a couple of chapters before, like on incest and stuff like that, which, I suppose if you're working in the tech industry in certain cities, that makes some sense, but it was a little bit difficult to apply to your vocation in,
Maybe I need to work for HR instead.
what's up?
Maybe I need to work for HR.
Seriously. Okay, so all those are up. So they are due the Sunday at midnight each week. So this first one is due this coming Sunday by midnight. This one's due a week later, Sunday at midnight. So you can do them early, but you can't do them late. Get it? Yeah.
So I was just looking at the tech talks and looking at the dates. So the last two, it looks like they're not on a Wednesday. Is that correct?
Correct. Or I think only one of them is not on a.
The 11th is on a Monday.
No, it's possible.
The 26th
Yeah.
on a Tuesday. Okay, I just
Because there was a double
correct.
booking. There was a double booking in the room. Yeah, the dates are correct on the tech talks. We tried to keep them all on the same day of the week, but there were a couple of little things we had to change around. All right, I think that's it. So you have 14 assignments you can do right now if you want to. Keep in mind your grades worth 60% of your grades homework assignments. So that's a lot of stuff. Then there's another 8 assignments accounted for across the 2 hackathons, right? It's worth 8 assignments. And then those tech talks are each worth 1 assignment. So that's another 7 assignments. And that isn't even dealing with the assignments for the coursework yet.
Let's get on it.
All right. So we're good to go? So what I'm going to do is, and I'll probably deviate sometimes, but I'm going to try to stick to, I picked, if you've had my class before where we have these things called Zhai Books, I wanted, because I have 2 8-week kind of sessions here, I tried to pick things that will fit into 1 week the best I could. Some of them might be a stretch, but we'll just deal with that when we get there. But you see roughly there are 8. This appendix thing actually has a bunch of architecture stuff in it. But so we're going to roughly do 1 chapter per week. So whatever we can't cover in class, well, regardless, you will, as a reading assignment and a homework assignment, will be going through the interactive exercises for each of these chapters. So you read through the chapter, there's some stuff in there where you can answer questions about different things. Like, here, a 0 or 1 is called a bit. You can check your answers, stuff like that. So it's an interactive type thing. How many of you have never used a Zhai book before? Is it most of you? Or some of you? You've used one before? Okay. Yeah, so
I don't have like the 201 pin on my laptop.
you don't have access to it anymore.
I don't.
Yeah, but in general, they're pretty good. But you need to make sure you actually use them. So you can go ahead and just assume that each of the first 8 weeks, each of the first 7 weeks, you will have a chapter from the Zhai book to go through. There may or may not be a direct assignment related to the whole thing, because there'll probably also be a programming assignment or some related assignment to what we discussed in class, but I don't necessarily know if I'm encouraging you to go ahead, but you certainly can. You just might want to review on the week that we are covering that material, just to make sure it's kind of fresher in your mind, something like that.
Are you able to like customize those like chapters? Like, are you handpicking those chapters?
Yeah.
Really?
Yeah, well, yeah, especially when you consider, so I've been using the Zhai books for a while, so I didn't help them build the company, but I've been with them since very early on. So for this class, notice the name of the book is Assembly in Data Science. That's not a book you can get on Zhai Books. So when you go in there, I kind of went through with them and said, okay, well, what makes sense for these things? So I picked the first 8, and then the second bunch is...
Yeah, because I was like, chapter 8 is the appendix, that makes no sense.
It just happened to be the name of the chapter that had the MIPS simulator in it, because we're going to be doing MIPS assembly in here. I actually prefer a different assembly language. I prefer the ARM assembly language, but some of you have had our undergraduate course where we did ARM. So I at least wanted you to have something new, although we will be doing something very different in here anyways, even from just an experiential stuff. And I have a feeling that a couple of you will be excited by it. So... I told her earlier that I had a surprise for her.
No way.
Oh.
She doesn't know what it is yet. I don't know if it'll be a stressful thing or a, oh my gosh, my life is over thing, but Well, here, we're going to be using a programming language in here called Scheme. Like Scheme? How many of you have heard of Scheme before? Several of you have had Scheme. You're going to have the advantage of being able to double dip from both classes, even though we're doing very different things. I typically use Scheme in my programming language theory class, where we write a programming language. In there using a functional language called Scheme. Well, this kind of language, assembly language, we're going to write our own assembler that's going to mimic the MIPS assembler, is a low-level language. So we're going to be creating the magic tricks that go into our CPU using Scheme functions. And it should be fun, but as I start introducing Scheme today, I think prepare for it to be a little different. How many of you have never used a functional language, functional programming language before, or don't know what I'm even talking about when I say a functional programming language? All right, good. So, how many of you have heard of a language called Lisp? Have you heard of Lisp before? Okay, so Lisp is a kind of an older language that's was designed to be, well, it was originally leveraged for artificial intelligence types of applications. Scheme is a superset of Lisp. So it has everything that Lisp has in it, and then some other things. The one thing I'll throw out there, because it's fun, Scheme technically supports, Lisp does not support loops. Scheme technically has a hack that allows you to do loops, but you're not allowed to use it. What that effectively means is that to accomplish loops in Scheme and in the homework, the programming assignments in this class, you'll have to accomplish them through recursion. Okay, what's recursion?
It's in it calls itself within itself.
Okay, so when a function calls itself from within itself, or a method calls itself from within itself. So the idea would be, let me just actually open up our slide set here.
No pictures on your slides yet?
This is all this. Well, actually, technically, I did prepare. You said, oh, yeah, she was saying, oh, did you put something on your slides? I said, oh, like, do you know me? Like, you know, like I pre-prepared slides. Well, technically, I did, because I already have the link to this up on, but I only prepared the front slide. So let's kind of start talking about some of these things at the high level, and then we'll start jumping in to stuff. When I say architecture, what am I talking about? What is computer architecture? This kind of falls into these categories. A lot of tech words seem like they're really common words, but we don't necessarily know what they mean. So when I say computer architecture, what am I talking about?
Hardware.
Okay, what kind of hardware?
So, like
What are examples of hardware?
like a CPU, memory, input, output.
Okay. So technically, computer architecture refers to any of those different kinds of hardware. You have various architectures. A lot of times when somebody says computer architecture, what they're really talking about is CPUs. That's probably what they're actually talking about. How many of you in here have built a computer before and had to buy RAM for it? And you had to get the right RAM, right? DDR3, DDR4, PC, blah, 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 blah. Okay, those are different architectures of RAM. Okay. Typically, though, when we talk about architectures, we are usually referring to processors. Okay, but it does encompass everything. So we can say any hardware has an architecture. And architecture is really a fancy way of saying, how does it work? Right? How's it put together? How does it work? All right. Typically, we are talking about CPUs. So what are some CPU architectures that you've heard of?
I can tell i7s.
Okay. CPU architectures. All right, so we have a company called Intel. So Intel is a company, and they have a processor architecture core called the Core i7 processor. And they've actually stuck with that for a while. So now they just keep throwing in, 6th generation, 7th generation, 8th gen on that. So let's just I'll put a few of them. We'll say 6th gen, Core i7, 7th gen. That'll work. And we could say i7. We could also say i5, i3, i5, i3. Starting with the 8th gen, we have an i9, an i7, an i5, an i3. All right, then we have AMD processors. Another company that makes processors. They're roughly compatible with these, let's say. We'll talk about that in a few minutes. But these are our kind of latest, greatest. You go to Best Buy, buy a computer today, it's going to have a Core i something in it. Or it's going to have an AMD Threadripper something in it, right? That's AMD's current cool name. Who wouldn't want a processor called the Threadripper? Sounds so much more fun, doesn't it? Like i7 or Threadripper.
More fancy.
Yeah, there's like no contest, right? All right, so, but if we go way, 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 way back, what are some of the old CPU architectures that you maybe have heard of? Pentium. So we have the Pentium processor, and then we'll put in Pentium 2, Pentium 3. We had some Celerons. Celeron processor. I have a funny story. Did I ever tell you about my dorm fire story for Celerons? Heard that one?
Yeah.
The guy lit his whole room on fire? Yeah, when I was in school, there was a famous processor. The first series Celeron processors came out. This was when Pentium 2s were out. So this was the Celeron is like the budget pleaser version of the Pentiums. And this was a 200 megahertz processor. So our processors today are like 3 gigahertz. So this was a lot slower in terms of number of instructions per second, let's say. But this one processor was famously overclockable. Like it had no protections in it. And the motherboards back then, so our motherboards today are smart motherboards. So they have things that take the temperature of the processor and all this stuff, and they'll just shut down if bad things are about to happen, right? Not back then. I mean, this guy, the motherboards, they had like jumpers and stuff on them. So you had to use needle nose pliers and, to set the clock speed and the clock multiplier. And then, he had like paper clips and stuff wrapped around stuff to like bridge gaps that weren't meant to be bridged, stuff like that. So he had this 200 megahertz processor overclocked to like 1.2 or 3 gigahertz. Usually you overclock a processor like 15%. This was orders of magnitude. So it was like 4 a.m. some night. You get off the elevator. I'm the first door on the right. He is the very, 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 very last door on the left. So it's probably, 200 yards or something down the hall. 4 a.m. he comes banging on my door. I open it. I'm up. I don't remember what I was doing. I was writing software or something or playing games. I don't know. He's like, I need help. So I come out of the room, turn right, and there's just flames billowing out of his room. This is not like a little fire. His entire dorm room was ablaze. Lost cause. This was a total loss. And then, but even back then, all the people on the floor, they had to split the cost of the repair.
Really?
Yeah, it was like $700. It was my cut of fixing this guy's inferno.
Wait, your cut was $700?
Yeah. It had to replace an entire dorm room.
Didn't you say something along the lines of like the door frame was like the only thing left standing?
Because it was made of metal. Yeah, I mean, the whole place was melted. You could not tell that a person or things were in that room before. Everything was ash. It was awesome. Nobody got hurt though. Yeah. So punchline from this class's perspective, heat is the enemy. So you always want to have good coolants on your hardware. All right, so anything older than Pentium?
I can't remember.
So we had like a 8086, 286,
Oh,
386,
486.
486. You guys have probably seen something before that says like x86 at some point. You download like a version of Java or something like that. It might say the x86 version. That kind of thing. So that kind of is referring to usually an Intel-based processor. But let's just kind of leave it at this. So, and I'll even take the 8086 off here just so the font gets a little bit larger than these.
I think x86 means it's like everything is new Intel CPU is compatible with x86.
Yep.
Doesn't mean it's exactly the same.
Right. So the idea here is that all of these, if we put these in order, so 286, 386, 486, then we have those. And we're skipping a couple in the middle here, but let's just kind of throw it like that. So this would be in historic order. All right, so 286 isn't the oldest processor, but that's what we're going to say is as far back as we go. 386 was the first processor that had a math coprocessor built into it. I think the 386 SX2 had a coprocessor built into it. But in any case, let me ask this question before we fill in that blank. What is a CPU? Those of you who've had my classes before should be able to answer this. What is a CPU? When we think about a CPU, what is that guy? It's a compiler. I don't even know if I could stretch that one to be right. Something with magic tricks. Okay, what's a magic trick? So a CPU is a collection of magic tricks, right? And I call them magic tricks. Because the idea is this: so as a human being, we know how to do a whole bunch of things, right? Okay, so if I put my hands, so everybody put their hands up. All right, so wiggle your thumb like that. Man, everybody can do that? I thought I was the only one. Can you do this? Now, what if you do both those together? So none of those individual moves are overly impressive in and of themselves. But you do enough of those little moves together, all of a sudden you can grab a cup, drink, things like that. Okay, so if we think of ourselves as being like a CPU, we can solve all sorts of problems by using our little tiny magic tricks that we know how to do, and we do them in a very specific order, and all of a sudden we can solve more complex problems. Make some sense? All right, so a CPU is a collection of magic tricks, which means there are a bunch of hardware-based solutions to very small problems on a CPU. These do very little on their own, but when called in bulk in a specific order, a quote real problem might be solved. Okay? So we want to think about our CPU as this resource, this go-to guy that we can say, perform magic trick 1, 17, 23, and 9. In that order, and something happens. Okay? When we talk about these different architectures here, with 286, we had, I'm just going to make up a number. Let's say we had 100 magic tricks. With 386, we had those same 100 magic tricks, and then maybe we had 20 more. With the 486, we had those same 120 magic tricks, but then maybe we had 20 more, so on and so forth. So we would say that our newest processors today are, roughly speaking, supersets of historical processors. All right? Now, that's not 100% true. I know this doesn't really happen anymore, but when you used to go into Best Buy to buy some software, you pick up the box, on the side of it, the box would say minimum software requirements, minimum hardware requirements, right? It's still on there. If you go to, pick a latest, greatest game. Here, let's do World of Warcraft. Minimum hardware requirements. So, system requirements. Just going to give it to me in something I can read. All right, this will be good enough. All right, so we'll just look at this one. So, processor for this World of Warcraft game, minimum requirements is, I'm just looking at the processor here. All this other stuff makes some sense, and we'll talk about that in a second. But only the first two are going to be meaningful to us. All right, this requires an Intel Core 2 Duo or an AMD Phenom 2 X3720. So the Core 2 Duo, that predated all of those i3, i5, i7. So before first gen i3, i5, you had a Core 2 Duo. That was our first dual core processor from Intel. So that guy would have been somewhere down the list, several more steps. Actually, he would actually be somewhere after the Pentium 3. We had the Core Solo, we had the Core Duo, somewhere in there. All right. And that's leaving out like Xeon processors and some of the other things in there. But it says the minimum requirements was this Core 2 Duo. The recommended specifications are at least a Core i5, third generation. That's what this 3 number means. It's third generation Core i5. All right. What does that mean? What does it mean for this to be the minimum requirements? Why do they say, hey, it would be great if you had a Core i5 third gen, but the minimum requirements is this guy? Why can't the minimum requirements be a Core Solo, the guy that came out before the Core 2 Duo?
Part of related to architecture, but I think mainly because of the performance.
Okay. Let's flip that. We're going to say it's definitely related to the architecture. This recommended specifications over here is performance. Okay. They're saying, look, if you want the game to, quote, run, you should have at least this. If you want the game to work, you should have at least this. All right, so it is an architecture thing. So I've mentioned that these guys are supersets of the guy before them. But at some point, so now we'll go ahead and throw Alexis's compiler piece in here. So you were like 5 minutes ahead of us. Okay, what's a compiler? Don't say a set of magic tricks.
It takes high-level language and takes it down to assembly language.
So this converts a high-level language into a low-level language. And for those of you who didn't have your original programming classes with me, I usually have a slide like this. There are 3 kinds, I have a bunch of slides like this, kinds of programming languages. We have machine language, we have low level, we have high level. What's machine language? Zeros and ones. Okay, also known as information as bits, the very first part of this. Okay, we're not going to escape zeros and ones. In fact, we're going to be working with them quite a bit today. What's a low-level language? Okay, assembly is an example of it. But what are the traits of a low-level language? What differentiates a low-level language from a high-level language?
Something human can read.
Human can read either of those.
Isn't it object oriented?
No.
No, no.
Operations?
Who?
Operations?
Tell me more about that. It's possible you're not wrong.
Is it?
It's an assembly, it's also to have more operations and you can have and or
Is it like a CPU memory? The language CPU is
Let me do this real quick. Let's do hello world assembly. I like this one. All right, so this is hello world written in assembly language for the Linux operating system. So we're going to go ahead and say that this is x86 assembly. Just leave it at that for right now. But it's specifically related to the Linux operating system. Now remember back over here on this minimum system requirements thing, I said we were going to kind of focus on these two here. All right. Now this course, first 8 weeks of this course, are largely about the processor. But things aren't so cut and dry anymore. Way back when we first started using computers, everything was about the hardware. In fact, you had the famous Microsoft quote. You know, one of the most lucrative deals in history was made when Bill Gates went into the meeting with IBM. What did Microsoft effectively invent with regards to software? Anybody know? Like, what's Microsoft's claim to fame? Well, you could say it's like Windows or something like that.
DOS.
It's the idea of licensing software. Licensing software. So Bill Gates goes into this meeting with IBM. Back then, IBM was the cool kid. And this idea of personal computers was just starting to become a thing. And Bill Gates said to him, you know, what we want you to do is your hardware isn't going to work without our operating system. That's what they said, right? Can you imagine having a computer in front of you today where you only had hardware? You don't have the Mac OS, you don't have Windows, you don't have some fancy schmancy piece of software that allows you to actually interface with the hardware. You had to work with it directly. That's not how humans work with computers today. We did a long time ago with vacuum tubes and stuff, okay, but you need a operating system. So Microsoft went in and says, you know what, IBM? You're going to need our operating system for your computers to run. And IBM says, okay, tell me more. But then Microsoft said, you know what? We're going to make this easy for you. Because IBM, they obviously, you know, they want to be part of this whole personal computer revolution in case it turns into something. So Microsoft said, we're going to make this easy for you. You only have to pay us for our operating system when you actually sell a computer. If you're IBM, doesn't that sound like a good deal? IBM's like, I don't need to invest in $1 zillion for this operating system. Every time I sell a computer, I pay Microsoft for their operating system. No harm, no foul. Famous quote from IBM. No problem. Real money's in the hardware. The real kicker. Anybody know what the real kicker with that conversation is? The Sheldon version of the historic bazinga to that conversation. Microsoft didn't even have an operating system.
Oh, yeah.
So he got IBM to agree to pay them on a per machine basis for an OS that they didn't have. Modern computing is built on top of a lie. Isn't that interesting? They say fake it until you make it. The side story to that is after they made this deal, then they had to go find an operating system. So I guess there was some rumor this guy who ran this little like tech shop had written an operating system, like 'cause it's just a hobby. It's like, oh, it'd be cool to write an operating system, and they went in and offered him $50,000 for an operating system called DOS, disk operating system. Now, if you're sitting there in the, what year would have this been? Mid 80s, maybe? Whatever, somewhere in that ballpark, some vintage 80 something, and somebody walks in off the street, and you're basically hawking. You're like a low-level Radio Shack. Okay, that's what you're running here. Somebody walks in off the street and offers you $50,000 in $1980 for the software that you wrote as a hobby. What do you say? You say yes. Okay, did Microsoft make a couple bucks off of that? Mm-hmm. They did all right. They did okay. All right, so going back to this, so kind of keep a couple of those things, not so much the trivia stuff. I mean, that's fun to think about the history of it, but the things I want to think about here as we go through this is CPU architecture, what that means, and then what an operating system is. What does that mean? Because what I'm telling you right here is what we're looking at is a low-level language. So that's that we're looking at. This is called assembly language for a program that solves the problem of printing hello world to the screen. That's what this program does. All right. So it's a low-level language that prints hello world to the screen on Linux using the Intel architecture, Intel x86 architecture. So let's just walk through this and understand how this code works. I know some of you have had class with me before, have actually seen this exact code. You want to walk through it and tell me?
I'm good. It's been a while.
You didn't memorize this? Everything I say is gold. You should just commit it to your soul. You didn't. What did you just ask her?
I said I thought you liked this stuff on.
I do. I think it's fascinating.
All right. So forget about this crap up here. These are just section delimiters. Program starts here where it says start. All right. Now, how about I give you a quick little punchline? We'll fill in the low-level language. Low-level languages have a one-to-one relationship with the CPU. Every instruction in a low-level language translates to exactly one magic trick on the CPU. Okay, I think that might have been kind of what she was getting at. It's like number of instructions or something like that. Assembly language programs are a lot longer. I mean, if we were writing in Python or Java, hello world is system.out.println hello world. Shorter than that. Okay? And would we agree that hello world is a very simple program? Okay, so this is a lot of code to do something so simple. All right? So each one of these instructions is telling the CPU to do exactly one thing. That or that. Little tiny little moves. All right? Now, the first four are actually all the same instruction with different inputs. Think of move as like a function call. Okay, so it's a function that takes something to move and the place you want to move it. All right. Down here at the bottom, this is our data section. So this is where you define variables in assembly language. Right? We actually are, I was going to say we're not learning assembly language in here. We actually are, but we're not learning this assembly language. We're learning MIPS. But these are some variables. So we have a double byte called hello world, and then we have the length of that guy. This is equal to the length of that string. So we have two variables, MSG, that's the message, and then the length of that message. So up here, we're going to move into all these EDX, ECX, EBX, EAX. These are things that are built onto a processor. Think of them as hardware variables. Okay? They're super fast memory that lives right on the CPU. So they're the fastest place that you could store a piece of data. All right? So we're going to put into this little bucket this value. We're going to put into this little bucket this value. We're going to put into this little bucket that value. And then this little bucket that value. Now, why did we do that? It has to do with Linux. Go back here. Oh, sorry. Minimum system requirements here for this video game we saw requires Windows. Is actually funny how their minimum requirements are 3 different operating systems. I don't think that means what they think it means. So they're saying the minimum system requirement for this is you need to at least have Windows 7. Although, in their defense, if you go back a few years before this, you had Windows 95, then you had Windows 98, then you had Windows ME, which you can then upgrade back to Windows 98. Yeah, that's kind of was the death of, because for a long time you had 2 different lines of operating systems from Microsoft. So you had Windows 95, you had Windows NT4. Then you had Windows 98, you had
2000.
Windows 2000. A lot of people thought Windows 2000 was the upgrade to Windows 98, but they actually were not the same operating system. Windows 2000 was built on top of the NT kernel. Windows 98 was built on top of the 9X kernel from Windows 95. So then Windows 98 came out, which was the upgrade to 95. Then Windows ME came out, which was the upgrade to 98. And that was not an upgrade. In fact, like Dell computers gave you a free upgrade back to, would send you the disk and stuff, but that was effectively the death of Microsoft's consumer OSs. From that point forward, Windows 2000 became Windows XP. So from a consumer's perspective, Windows XP was a really good consumer operating system. It was it's actually probably to this day, Microsoft's most successful operating systems. Probably a pretty close thing between XP and Windows 7. Yeah. And I think Windows 10 is going to work out okay. I mean, it seems to be doing all right. Well, that's what I'm saying. So Windows XP, Windows 7, but Windows XP is really important because Windows XP was actually the upgrade to Windows 2000. It was built on top of an operating system called the NT kernel instead of the 9X kernel. Okay, what operating system are you running right there?
10.
Nope, you're running the NT kernel.
Well, yeah.
What operating system are you running? NT kernel. What operating system are you running? Not the NT kernel, you know? So you're running the Mac OS, right? So you're running on top of OpenBSD Unix. It's a Unix kernel. BSD Unix is the kernel. But now when you said Windows 10, that's actually your distribution, right? So you have the core operating system is the NT kernel. The core operating system is the BSD kernel. And then on top of that, we expect there to be a whole bunch of applications that ship with that, right? When you first get a Windows laptop, you expect Notepad to be there. You expect a web browser to be there so that you can quickly download Chrome and replace it. Look, I need to be able to imagine if they didn't even give you a web browser and you couldn't get anything except Edge. They give you his key where
There's no Edge, not downloadable.
So when we think about OSs as humans, we typically are thinking about distributions, right? We expect an operating system to ship with a text editor, a web browser, some general things that allow us to solve kind of common problems. And then we can go and pay and install our more specialty software, Microsoft Office, video games, things like that. All right. But when they say operating system, commonly people do refer to Windows 10 as the operating system, Mac OS as the operating system. Just technically under the hood, the OS is the kernel. All right. So just so this doesn't get too stupid here, we're just going to say Windows 7 was the minimum operating system requirement for this game. So you had to have at least Windows 7, and you had to have at least an Intel Core 2 Duo processor. This is the hardware architecture that was assumed. This was the software, we're going to say architecture, that was assumed. And what does that ultimately mean? So keep that in mind for a second as we go through this. So we move 4 pieces of information into these various buckets. Then we interrupt the CPU and we say, kernel, take over. Call the kernel. What does the kernel do? Now notice they gave us a couple of things over here that when we loaded the number 4 into EAX, we were delivering, well, we were kind of hiding something for the operating system to find in a minute. We were saying, by the way, OS, I know you're going to come look here in a minute. And when you come look here, you're going to find a 4. I know that 4 actually means syswrite. Write something out to the system. That's a computer program that's built into the operating system. So, very first thing we did, we interrupted the operating system. The kernel goes and looks in this bucket. It finds a 4. It says, oh, we're writing some stuff. Syswrite. And it says, okay, now I need to look in 3 other places. Because in order for syswrite to work, it needs 3 inputs. It needs to know, where am I writing it? What am I writing? Well, where's the beginning of what I'm writing? And how long is it? When do I stop writing? All right? So it's saying we're going to write to standard output. This number 1 is related to the Linux kernel as associated with standard output, which is your monitor. Okay, this is going to write to your computer monitor. What are we writing? The pointer to the beginning of the message is stored in MSG. Okay, so this is our data byte. How many bytes do we write? This many bytes. So we have a function that is function 4, syswrite, that takes 3 inputs. And then it does the magic. Then we come back, CPU's back on running this program again. Next instruction, we move into EAX. Notice this is the exact same place that we put that 4 before. Now we're overwriting the 4 with a 1. And then we interrupt the processor again. What was the very first thing we did? What was the very first thing the kernel did the last time we interrupted the processor? It checked EAX. What do you think is the very first thing it's going to do this time when we interrupt the processor? Check EAX. So it's going to say, I'm going to look in EAX because EAX is where you're telling me what you want to do. And we find the number 1 in there. And 1 in EAX is related to the function sysexit, end program. And in order for a program to end, do you think you need any inputs? Or can program just end? That's why we didn't have to move anything else. No inputs are required for a program to end. Make sense?
Why? I have a question.
Go ahead.
Why on top EBX1, actually that EBX1 means it's the pointing to the monitor, but why EAX1,
Well,
this one?
Yeah. So, first of all, computers like numbers, right? We're going to see that over and over again. We're going to be always storing zeros and ones, zeros and ones, zeros and ones. This one and this one do not mean the same thing. They are both the number 1, but what we put inside of EAX, the meaning of what's in EAX is, what function do you want me to call? What we put into EBX here, relative to the syscall 4, is this guy should hold the where do you want me to write this? And let's say that there are 3 common places you could write something to. There could be more, but let's say there's 3 common. Sysin, sysout, syserror. 1, 2, 3. 0, 1, 2, depending on how the OS numbers it. So this one refers to bucket 1 of the array of potential places you can write stuff out to. This one refers to bucket 1 of my collection of functions, function calls. Same number, but means different things.
So such description should also belong to the architecture, right?
Yes, but this is the hardware architecture mapping up against the software. We're going to say software architecture, but I'm going to use a new word. I'm going to say software API. Okay, so let me draw a little picture here. All right, so we have our CPU. This is our collection of magic tricks. And human beings don't talk directly to the CPU. We talk to it through our operating system, which has a collection of system calls, which is effectively an API. All right. Then we have our assembly program, let's say. This is a collection of instructions that refer to magic tricks in terms of system calls. That's what our modern software applications look like. And if we keep going up the list here, we have our high-level code. Humans like this. And then in between there, we have our compiler. So we write the high-level code, we compile it, it turns it into assembly language compatible with, so that compiler needs to know two pieces of information. Oh, we're already on the compiler screen. So this guy converts a high-level language into a low-level language, needs two inputs. Needs two inputs. One is the target hardware architecture and the target software architecture, which OS system. Well, let's just say which OS. So it can target the correct system calls. Just as we said back here that the newest, latest, greatest processors are supersets of last year's processors, which are supersets of the processors before that, so on and so forth. There are changes. Sometimes we drop an old magic trick because it's no longer used, or maybe we had a bug in it, or we change the way it works. But typically, with a new architecture, because a lot of times what you'll see is like when you go out to Best Buy today, let's say, you're looking for a new computer. You can get the latest, greatest computer that has the 8th generation Core i7 processor, or for 40% off, you can get the laptop that has last year's 7th generation Core i7 processor. But when you look at the sticker on this year's, it says that it's up to 40% faster. Which do you get? What does it mean for this year's Core i7 processors to be up to 40% faster than last year's Core i7 processor? What's the difference between this year's Core i7 and last year's Core i7, just generically speaking?
Frequency is higher.
Potentially. Not commonly anymore, right? Don't processors pretty much sound like they're roughly the same speed today as they've been for the last 8-10 years? In fact, sometimes you get the newer processors actually slower than last year's processor. Possibly more cores, but even that's not super common. Quad cores were very common for a while, right? So what's actually different?
Then the command collection,
So did they add anything new?
more magic tricks.
Possibly more magic tricks.
Or better magic tricks.
Yeah. Either improve or optimize an old magic trick or put more magic tricks. Well, if they had room for more magic tricks, why didn't they put them in last year's processor? Why didn't they have room for more magic tricks last year? Why should you have to pay more money for this year's processor that has more magic tricks? If you looked at the processor, a couple of you said you've built machines before. Have the processors drastically or even at all changed in physical size in the last many, many years? No, they're all physically the same size. An inch and a half by an inch and a half, something like that, a little square. Why can we fit more magic tricks on this year than last year? Is this just Intel sticking it to us? Or AMD? Because you're right, there are some new magic tricks on this year's processor. And a couple of those new magic tricks really optimize certain things and might, in a very specific application, give us up to 40% increased performance. They give us millions of times increased performance on things that the last year's magic tricks couldn't even do. But why is there more space now than there was last year?
Maybe it's because last year it's not necessary to have those tricks.
Well, then why is it necessary now?
Because new operating systems, new application comes out.
Oh, so you think maybe they had space for them?
No, what I mean is, so typically we build software based on hardware, but due to we have new software, then the hardware trying to help the software to go better. So they improve based on the software newly invented.
Yeah, so that explains the issue with optimizing old magic tricks. But all of a sudden they're adding new ones? I mean, don't you think Intel would have stuffed as much stuff as they possibly could onto last year's processor? I mean, typically if you buy some land and you don't need a front yard, you build everywhere on that land, right? You want to use as much real estate as you possibly can. So, seems like it makes sense that Intel would have put as much cool stuff on there as they could, really packed it in, charge you top dollar for it, right? Because most of their sales are coming from the top companies, not from an individual. You know, very few of us give money to Intel. Intel gets their money from Dell or from Apple or, you know, the companies that sell these computers, HP. If you look at the latest, greatest processors, a lot of them will say something like 7 nanometer technology. Last year was a higher number than that. What does that mean when we say 7 nanometer or 8 nanometer or 12 nanometer or 14 nanometer? What's that referring to?
The size of the string.
Okay, so our processors today are effectively printed circuit boards. You know, some mad scientist somewhere went in, they created a prototype of our processors, right? So in some laboratory, there is a 9th generation Core i9 processor somewhere that has all these wires. I mean, it takes up the whole room like this, probably, just wires everywhere. Okay, that's not ultimately what's going to ship in your laptop. That's the prototype with that for them to solve the problem before they go to large scale integration and mass production of that type of thing, right? Okay, but when they go to mass produce it, they have these machines that effectively print all the little circuits, right? All those little magic tricks, they're printed on there. Now, the smaller the nanometer, the more magic tricks you can fit in the same space. Think of this as like the width of the line. You called it a string, right? So if you have a pen and you can make really, really, really slender lines, and you had, hands that were, like you could actually draw lines right next to each other that weren't touching each other, but you could write really, really little tiny lines. The more lines, the thinner the line, the more lines you can fit in the same physical space, right? Okay, and then the kicker is, we said a while ago, who's the enemy? Heat. Heat's the enemy. So now you got more stuff on there. Now you got to figure out, okay, well, is this more stuff going to make it hotter? If so, how do we cool it off? So one thing you will see as these newer processors come out, and especially the desktop processors, you'll start seeing, I mean, in the early days, you had these heat sinks that were just, didn't even have a fan on it. Just a little tiny metal thing you put on top of there. That's good enough. It's fine. The original MacBook Airs just had a metal heat sink. Okay, now you get one of these laptops and you think the thing has no moving parts, and all of a sudden sometimes you just hear this fan just crank up, right? Just going nuts. So if you look inside, in fact, remind me when we go down and look at the new space, we have a couple of the 48 core AMD EPYC processors in there. You can see what the heat sinks on these things look like. Okay, it basically looks like there's a football sitting on top of the processor. This thing is moving air. And there's a whole bunch of like tubes and stuff going different. It is doing everything it can to move heat away from that processor. Because that's the only way to keep that processor from damaging itself. That's how hot they get. Okay, so trade-off comes somewhere. You want to fit more circuits on there? Fit more things in there? We have better technology for printing more stuff on there? Fine. It's going to get a lot hotter. So now you got to have a way to cool it. That's a lot easier problem to solve if you have a big old desktop system where you can put a giant fan in there or something like that. You know, my buddy in college, he had just a bunch of the fans that go back and forth. You get like from Walmart, just pointing into his case. That didn't help. That probably blew the flames around. But with the desktop computer, you have room where you can put a big fan. These laptops, they keep getting thinner and thinner and thinner. I mean, this machine has a Core i9 processor in it. And sometimes I'll hear the fans kick up. But this thing, it can turbo boost to something crazy, but most of the time it's going to run at the lowest speed that it possibly can to keep up with what you're doing. So the operating systems try to be very smart in terms of how they're scheduling the CPU. All right, so we keep getting better and better and better at printing stuff smaller and smaller and smaller, and that's why we can fit more and more stuff in the same real estate each year. And we get more magic tricks, which then gives us the possibility for very, very specific applications to have up to 20% faster, 40% faster, 70% faster. And they can say up to 40% faster because if there's one example of something that can give you 40% more speed, they can claim it. Even though for 99%, possibly 100% of the things that you actually do, last year's process, or the year before that, or the year before that, or the year before that might perform just as well for you. So you might as well get the budget pleaser price. So a technologist would go and look at what specifically is faster about this generation's processor and see, does it benefit me? Unless somebody else is footing the bill, then just get the newest, greatest, latest, greatest. Right? All right, so questions about any of that stuff? So we understand this idea of what a CPU is. We understand the idea of high level versus low level. Low level is a one-to-one relationship. What must high level be then? One to many. So we write one line of code, system.out.println hello world, and it translates into something like this. Lots of lines of code. Who does that? The compiler does that translation. And the compiler needs two pieces of input. It needs to know what architecture am I targeting. So I use the right instructions for that architecture. And what software architecture am I targeting? Which operating system? Because you also need to do it in terms of the API, the system calls for that particular operating system. Because as we see right here, the hardware architecture and the software architecture work together to solve problems in our modern computers. Make sense? All right, so let's take, like a 2-minute break? Let's take let's take maybe 5 minutes and then come back, and then let's walk down to the new building and I'll show you that, then we'll come back and pick up.